Okay. Um, I want that somewhere else. I want that somewhere else. It's a great first line for a movie, don't you think? We don't edit anything. Um, right. Okay. Bit of a new topic today, but I think you'll see conspicuous echoes of some old topics. Uh, and what's more, it might even be quite useful. We're going to talk about an idea, a modern convenience. Well, actually, it's 1970s technology that works. In fact, it's older than 1970s technology. I think it's actually 1950s technology. Um, um, so these things are regular expressions. And regular expressions are a little language. It's a simple little language for describing strings that you like. So strings, sequences of characters. Do we like this string? For example, the thing you see before your very eyes that, that makes defined show up in bold font with the green background. That is that way because a helpful friend um, uh, wrote a bunch of regular expressions to say, when you find a string that's like this, color it that. So our lives as computer scientists are full of gadgets made from regular expressions. They are, they're not by any means universal in terms of describing texts that you might be interested in. They're not even as powerful as the grammars we learned in semester one. Their main virtue is that they're cheap. They also have some quite nice mathematical properties, and we'll explore a bit of both. Okay, so let's walk in. We're going to be needing a bit of Boolean logic, so I've given us our usual type of bits and the Boolean operators double bar or and double ampersand and to distinguish them from the proposition formers. And we've got lists. So a list is a sequence of things. This A is a variable that stands for the type of the elements in the list. So all the elements in a list have the same type. A list is either empty, that's the list made by nil, or it's got a first thing and some more things. And we put a single colon in between the head of the list and the tail of the list. And I'm kind of routinely livid at this notational choice, but it is standard and I'm stuck with it. The problem is that colon is a symmetrical operator. It's got left-right reflective symmetry, but it's not a symmetrical notion. It takes an element on the left and a list on the right. And this confuses beginners the world over. And it's an easy way. I do this rant in a room full of academics, and half of them nod vigorously, and the other half look at me as if I'm nuts. And the half who nod vigorously are the half who have ever demonstrated this stuff in a lab to undergraduates and actually seen the confusion this terrible decision causes. um, so that's unfortunate. But yes, the other thing is that this operator made from a single colon is pronounced cons, which is short for construct. And there is a rumor that my father named me after this operator. It's Connor, short for constructor. Actually, that's a complete lie, but never mind. Actually, it's not a complete lie, I fear to say. Right. We are also equipped with the concatenation operator. Oh, I should say one thing. if I haven't made it clear enough already. So you know in ask, if it begins with a capital letter, it's just a thing, right? Something, a name beginning with a capital letter stands for a thing which has its own independent existence, like a new invention that is itself, like a proper noun.
Such as list.
Such as list here, and nil. Whereas a thing which begins with a lowercase letter always stands for something else. So the little a stands for whatever type you're going to use for the element. This is an important reading thing. Okay, there's a similar convention for infix operators. So infix operators are made from clumps of symbols like this. So if the first symbol in such an operator is a colon, then it's a constructor. Then it's like beginning, that's the infix version of beginning with a capital letter. And if it doesn't begin with a colon, it's standing for something else, standing for some two-place function. And of course, colon begins with a colon. So you know, it's the thing, it's the original constructor, right? You know, before, when it basically, yeah, that's 1950s technology as well. Okay, so we've got so this double plus, bit Orwellian, is also standard notation. It's the append operator, which concatenates lists, and you can see it deserves to be symmetrical. It takes a list on each side. Okay, so I've proven some handy facts about lists, which I'm going to ignore, because I want to get on to the good stuff. Okay, so we're going to introduce regular expressions a little bit at a time. So we're going to write down a data type of regular expressions. I might actually use old-fashioned chalk to draw on the board what these things look like in real life.
Be careful for the online crowd.
Yes, it's true. And they'll only get a tiny picture of it. So maybe maybe I can write something in comments. Okay, so we're going to take it in turns to introduce the components of regular expressions. And I guess I'll go first. Okay, so the idea is that, the idea of a regular expression is parameterized over whatever alphabet of symbols you use. The concept makes sense, whatever alphabet you're using. We are going to use a particular alphabet, which consists of A, B, and C. But you can have any alphabet you like. We could use bits, but I want to use bits for logic, and I just don't want to cause confusion. But the notion makes sense, whatever set of symbols you put in your alphabet. And then what's a string? A string is a list of those symbols, right? Possibly empty. The empty string is a string. Okay. And then a regular expression is something whose job is to describe strings you like. So I'm going to kick off. Oh, yeah. Okay. So we're going to define, as we define what the regular expressions are, we're also going to give the rules for when a particular regular expression likes a particular string. So that will tell you the meaning of the regular expression. Right? You know, which things it likes is what it's about. The whole point of a regular expression is to determine a set of strings. Okay. It's unfortunate that I've had to specialize this notion to our particular alphabet ABC. That's on me. That's a bug in Ask. It ought to be I ought to have a variable here and the same variable there. But it didn't like that yesterday, and I didn't have time to fix it. So you'll see there is nothing specific to ABC that will go in this definition. Okay, let's kick off with the first one, which is likes one particular symbol. The sim constructor of regular expressions packs up one symbol from the alphabet. And this in real life, you would just write the symbol escaped if necessary. Yeah, so when you encounter these things in the wild, you don't have a separate wrapper sim for the symbol. You would just write the symbol. Unless it's a special symbol, in which case you would write a backslash and then the symbol. Right.
So just to be clear, what Connor means by real life is systems that use regular expressions.
Yeah, you know, like if
you write the syntax highlighter in Emacs or search for a string in a file or something like that.
Yeah. So we're building a essentially Haskell data type that tells you the structure of regular expressions, but doesn't tell you how to write them. Tells you what it allows us to talk about what they mean. Okay. So the proof rule for one of these sim regular expressions. So likes sim a x's. Oh, that's another thing I should mention. There's a particular school of functional programming from which we come that habitually chooses variable names with particular endings to be suggestive of particular stuff. And if we want to make something look like it's a variable with a list type, then we will make that variable end with an S, and we will pronounce it like a plural. So here, X's is supposed to suggest some elements, right? So when does sim A like a string X's? When we can prove that X's is equal to A cons nil. So that's to say, the only string that sim A likes is the string that consists of exactly one A.
You need to name this proof rule as well.
I do, yes, I do. I have to say, by exact, I think is what we decided to call it. Okay. So we've got a symbol, right? So let's say prove likes sim A cons nil. What have I got wrong? I've forgot a closing parenthesis. That's legit. Right. So here we say by exact, and we're done. Isn't that nice? Under taste is distaste. I might do prove not. Why can't I type today? Likes sim A B cons nil. Okay, I say by not introduction. And then I get told a statement of which I'm deeply suspicious namely that sim A likes a singleton B. So I say, how could that possibly be true? And ask tells me that can only be true if singleton B is equal to singleton A. And when someone hands us an equation which is obviously false because of a clash of constructors, you from it, and the goal goes away. So there we are. We have an example of singletons. Okay. So great. We can recognize strings that consist of exactly one symbol that we like. Let's see if we can extend that to slightly longer strings.
Right. So now I have to guess which one Connor wants me to do next. I guess you want one or then the other. Is that right?
Yeah.
And
yeah, colon ampersand.
Yes. So the idea of this regular expression is that we want to match one expression and then we want to match another one, right? So this way we can build up whole words by stringing symbols together, right? So I can say I want the first character to be this thing, then the next one to be this thing, and so on and so on. So this is going to be a regexp for the first thing, and then this is how we wanted to do it, right?
Yeah.
And then a regex for the second thing, right? So we need some way of describing the first thing we like, and then some way of describing the second thing, right? So that's the idea. And what's the proof rule? Well, to prove that P and then Q likes X's, then we want to say, right, what does this mean? Well, X's is a string. So if it's supposed to match P and then match Q, then we need some way of splitting up X's into two parts, right? And we don't a priori know exactly how this will work. We're just happy if we can split it somewhere so that the first part is liked by P and the second part is liked by Q, right? So what did we call this rule? Split. And right, what should I call these?
Y's and Z's?
Y's and Z's, I guess.
I mean, or pref and suff.
Yeah, right. Right, so in order to use this rule, we have to give this splitting of x's. So the first thing we need to prove is that x's is actually equal to y's followed by z's. And then we also need to prove that P likes the first part and Q likes the second part, right? So prove likes P y's and prove likes P
Q's.
Q, yes. Good. So my regex was P and then Q. So I want P to like the first part and I would like Q to like the second part, right? Yep, does that make sense? Right, I guess we should see if we can prove this. So I would like to show that sim B and then sim C likes the expression B followed by C followed by nothing. Okay, and how do I prove this? Well, I only have one way of proving that this something and then something else like something. So I have to say by split, and then I have to give the splitting. So I need to give the list that sim B likes, and then the list that sim C likes. Right? So I have a priori three choices. I could split with nothing for the first part and everything for the second part. I could split for B for the first part and C for the second part, or I could split for everything for the first part and nothing for the second part, right? but there's one obvious way to actually make it work, which is to make B be the first part, because that's what sim B matches, and to make C be the second part, because that's what sim C matches, right? So I'm going to say my first part is the list B followed by nothing. My second part is the list C followed by nothing. And then let's see what happens. Right. Okay, so then according to the rule, I had 3 sub-goals to prove here. I had to prove that my splitting really was a splitting on my original list. And I had to prove that the 2 sub-expressions liked the sub-lists, right? But in this concrete case, the fact that B then C then nothing is the same as B append C is just, that's just true by computation, right? So I don't get this sub-goal that ask is happy to just discharge that for me. But I still have to show that sim B likes this thing and sim C likes this thing, right? But that should now be by exact, I hope, in both cases. And indeed it is, right?
Okay. So that's cool. We can make longer strings. One thing it might be worth doing is to prove that if P then Q then R likes something, that is the same as P then Q then R liking something. So that's to say, you know, that's exciting. Yeah. So, you wish you never ever met her at all. You wish you never. I do hope whoever that is going to mute themselves. Right. So you see this thing. It's about it's about putting things side by side. And didn't we say that, putting things side by side is the classic example of a monoid that you've been living with your entire life, right? When you look at a shelf full of books, the only brackets you see are holding the shelf up. Right. So let's essentially demonstrate the associativity of this sequencing operator. I want to do that. That's by equivalence. Now, we didn't do this in rehearsal, so I might discover I regret this. But I think it should be all right. I haven't proven associativity of append. That's what it's going to turn into. But, well, let's do some of it. And in particular, we'll just do it one way round. Finish the job later. Could go in the homework, actually. Not a bad plan. Right. So what do we know if this, and I'll put the left nesting in. That's this way round. What does it tell us for this to be the case? It tells us Fred did a wonderful thing on the train yesterday. It tells us that X's must have been split up with P then Q liking A's and R liking B's. Well, I've played this game before, So I know I really want the x's that's in the goal to be rewritten. Okay. And now I can tell my next move is going to be to split this thing apart. And I'm already regretting my choice of variable name. Actually, I should have called this. Does it work over multiple lines?
Yeah.
Okay. So I'll just rename that to be Y's because you can see what's coming. I'm going to call this part B's and this part C's. So I've now split. I got that completely wrong. Yeah. Well, I'll run with it. I renamed the wrong thing to make a nice little proof. I should use my equation, and now I've got things with silly names. The danger of live theatre. Right. So now I've got that thing. I know that that left-nested PQR likes left-nested B's, C's, Y's. And I would like to know that right-nested PQR likes the same thing. Well, somewhere, I think I gave myself this handy rule, which you should not be surprised by, which is that if a regular expression likes x's and x's is the same as y's, then it also likes y's. That's a free hit, right? It's annoying even to have to prove it. But it's a useful fact, which I'm going to use here. And my regular expression that I'm going to pick is this one. And what do I want?
It's the Q on the right as well.
Yeah. And then I'm going to pick that thing and put it there. And then what do I, and of course, there. And then what do I want for x's? I want x's to be the other way around. Well, actually, I'm going to leave it like that because that's the, hang on. What have I been given? Yeah, I've been given lots of equations. Yeah, I'm going to leave x's as a variable because I can see that's the one I know is liked. Okay, so now I have to prove that by and in production. And oh, I got
I think you
yes,
just have to do it from scratch.
I have to do it. Yeah, I have to say from x's is yeah, I didn't, that was completely the wrong move. Live theatre. Right, I can tell I want this to be grouped this way. like that, I think. Get rid of that. Okay, so now I have to prove two things. I have to prove the right nested likes, and I have to prove this equation. So you've all proven that append is associative before, and then I'm hoping that this is by split B's and C's append Y's. And then this is by split C's Y's. Okay, I'm going to stop doing this because it's clearly a bad idea to improvise quite so crazily. But you can see, that it's exact, the meaning of our sequencing operator ampersand is given in terms of append, and the meaning, so ampersand will behave in an associative way exactly because append is associative. Okay. So let's have an easy one to recover from a difficult proof attempt. We've got an associative operator, and we've figured out how to scale up from matching one symbol to matching more than one symbol exactly. What's missing? You see an associative operator. What should you think?
What's the unit, right?
Yeah. What's the right way of doing nothing? How do we write something that recognizes that likes exactly and only the empty input? Null. We need a null. That's even what we're going to call it. So actually, I put a little thing there. Null. Everything's fine. And I give a proof rule for it. Prove likes null nil by, I think done was what we called it. Right. So of course, just by way of likes null nil, you will not faint with amazement to see that just works. And you would expect to be able to prove, for example, that likes p and null x's is equivalent to likes p x's and all that kind of stuff. So you can see there's some stuff appearing. There's a thing that behaves like and. Now we've got a thing that behaves like true. There's a thing that it kind of behaves like multiply, and this is a thing that behaves like one. Okay. So where should we go next? Oh yeah, sorry, we should do it in real life for the story so far. In real life, you usually write the null regular expression just as an empty expression, and you usually write the sequencing operator just by writing two things, one thing then another, no punctuation at all.
Right, so maybe we should do angry with everything. So contrast.
Yes, actually, that's important.
So this is one of the things that can be confusing with regular expressions. So we have an expression for the empty string, but the empty string is still a string, right? We might also want to have an expression which just doesn't like anything at all, right? And not liking anything at all is different from liking the empty string. So what did we call this? Nil?
We called it fail.
Fail, yeah, that's a good name. So we have a regular expression called fail, and we just don't have any rules for this thing liking anything. So it is never the case that fail is going to like a string. So it's never matching anything. And you could say, okay, what's the point of that expression? Well, the point is that sometimes you want to really, I mean, you want to be able to describe no strings, right? So regular expression is language describing strings. It's important to be able to say I like these strings, but the special case of this is not liking any string at all, right?
Yeah, I mean, you know, it's like if we didn't have a way of talking about the empty set, you know, when it turns out that we're unlucky all the time or whatever it happens to be. So yeah, we need ways to talk about failure modes properly. You'll see later on that we sometimes do various calculations that produce regular expressions that we then use to manipulate strings. And it has to, nothing has to be a possible outcome of those calculations. In fact, we will do that very soon.
Yeah.
Right. So you need to put the extra pipe
yes.
in position. And yeah, just to emphasize a perfectly typical mathematician's joke. If you're wondering why Fred didn't write a proof rule for fail, well, think of it this way: Fred has written all the proof rules for fail. Right. How do we say fail doesn't like anything? We say there's no way of proving that fail likes anything. So we're in a situation where we're using the fact that when we declare one of these relations, we are saying all and only the ways of establishing that the relation holds.
It way of actually proving not likes fail exists.
Yeah. Well, I was going to prove something slightly different. I'm going to define a thing called ensure, which takes a bit and gives you a regex. And this is the way of embedding a test into a regular expression. So if you're trying to design if you're computing a regular expression that that does a particular job, and as part of figuring that out, you're testing some sort of condition, then you can plug a bit of logic into a regular expression like this. So we look at what the bit is, and if the bit is false, we're angry with everything. And if the bit is true, then we're happy, but we don't eat any data. So if you kind of just plug that in the middle of something, then that behaves nice, pleasantly compositionally. And then what we want to say is, what do we want to prove? we want to improve that ensure that likes ensure be x's means the same thing as b is true and x's is nil. Does that seem plausible? Right. And I've been through this movie before, so I propose that we split this into two problems this way. And then we hit test. Okay, and now I'm going to say by equivalence in both places. And then I get a bunch of stuff. Okay. So in this case, I'm handed an assumption likes fail x's, of which I'm deeply suspicious. So I say, how could that possibly be true? Also, I can see that I really don't like the look of this goal, right? If someone's going to ask me to prove false equals true, I'm going to figure out how to get out of the situation. Likewise, this time I'm delighted because I can see I've been handed a false assumption. All I have to do is unpack it. And now I can nail the lie. Okay. So here, this way round, I'm being asked to prove that I is I, that'll be easy, and that X's is nil. But my big clue is that X's is liked by null. So, and that's handy because that gives me the other thing I was missing. So I could finish that off by and introduction, and ask will do the rest. Here, I want to prove that null likes something, and I just need to dig out and deploy the fact that it's the something I want. So I say from, and I feed in the and that splits the and into two pieces. And now I can say from x's equals null, and somewhere that just happened nicely. I think it's just the rule, because it has no conditions, it's just taken as a prior theorem. Okay, so we've checked that ensure does its job. If the bit is false, nothing matches. If the bit is true, only the empty input matches. Okay, it's 5:02. I think it's time to pause the recording and take a 10-minute break. See you at 5 past. Okay, folks. I checked the chat in the interval, and judging by the timing, someone in the audience as well as me had a rough time with this proof. By the way, Zoom folks, you are connected to the sound system, which means if you transmit sound, it will be heard. And sometimes that's a bad thing, but sometimes it's a good thing. Okay, so yeah, so let's just have a quick refresh. One thing I did in the interval was to just throw in the usual proof that append is associative. And now what happens here is our strategy starts off by saying we've got a left group sequence and we want a right group sequence. If we if we interrogate how the left grouping was even possible, then our list splits up into 3 pieces in a left group way. And I've now chosen sensible names for the pieces. So here, my original list X's, I turn it into Y's for the group on the left and C's just for the part that R likes. And then I split up the derivation that the left group for Y's happens, and I call those pieces A's and B's. And I couldn't have done that without Fred's fantastic renaming technology. So thank you, Fred. So that means we're in the situation where we're now, once we've done all the rewriting from the equations, we're left trying to show that the right grouped regular expression accepts the left grouped input. And what happened, what here is, we really wish that input was right grouped instead. So this is where we deploy the fact that if a regular expression likes some string, then it will like any equal string. So in order to deploy that, I then have to prove 2 things. I have to prove that I can still show that the right grouped string is liked by the right grouped regular expression, but I've got all the pieces to do that, which is why this proof is so nice. And then I'm hoping that if I just comment that out, now that ask knows append is associative, then this half of the proof is done. And I'm not going to do the other half because we've got other fish to fry. Okay.
So one thing I would maybe say is that there's one thing to understand the details of the ask proof, right? Which can get a bit hairy when you're in the middle of it. But it's also asking yourself, do you believe the statement, right? So if you just read the statement, ignore the proof for the time being, then it kind of says, well, if I have an expression which likes P, Q, and R, does it matter how I bracket these things? And the answer is no, it doesn't matter, because it's still going to be P, then Q, then R, right? And it doesn't matter how you split this up into binary something, then something.
Right. I think it was my go to invent something that does something. Okay. So far we've figured out how to say that we don't like anything, that we like no things, and we figured out how to say that we like one thing, right? Pick any string, you can construct a regular expression which likes only and exactly that string. I'm not going to do that here. You're going to do that for your homework. But you know, it's possible that we might want sets of strings that have more than one string in them. So we had better make sure that we can offer a choice. That's what we're missing. We've got something that's very Andy, and we've got a thing that behaves like true. We've got a thing that behaves like false, but we haven't got anything that's kind of ORy yet. So so let's do that. So I'm going to use an or-like symbol. In real life, you write pipe between the 2 options, or plus in some dialects. And yeah, you can usually use parentheses in regular expressions. And you have to be very careful of some of the symbols you want to match a parentheses and all of that kind of stuff. Okay. So that offers a choice. And let's then do prove likes P or Q X's. Well, I'm hoping that no one is going to faint with amazement that there are two ways that you can prove P or Q likes X's. You can go left and prove that it's P that likes X's. Or you can go right and prove that it's Q that likes X's. So I suppose we should have an example. Prove likes sim A or sim B. I'm very tempted to choose A because no, I'll choose B. I'll choose B so that we actually get a sub goal. So, okay, so here's an example. The regular expression likes a single A or a single B. We're feeding it a single B. I suggest we go right. And then how do I prove that sim B likes B nil? That's exact. And we've got a thing that behaves like or. We've got a thing that behaves like and. Do you think, so we're going to get monoid structure, right? The neutral element of or, of this or regular expression is going to be fail, right? You know, P or fail can't work if, oring fail doesn't make any difference because fail doesn't help. So we've got two monoids. We've got a kind of ori monoid, and we've got an andy monoid. And funnily enough, if you've got A, then a choice of B or C, that's the same of having a choice between A then B and having A then C. So you're going to get a distributive law. Shock horror. It's a rig. I mean, okay, how are we doing? Got an example there. I could just by way of doing a bit of distaste. Um, uh, further down. Uh, um, something like that. All right. So I want to prove that A or B doesn't like C. So I say by not introduction. And now I've got an assumption which I have to refute. So I interrogate, how was this even possible? It was possible in one of two ways. So we keep going. How are you even possible? And while I've got it handy, I'll just paste that and update that. Oh, in each case, we get a suspicious looking equation. How is this equation even possible? Oh, it isn't. How about that equation? That's not possible either. Okay. So we've got the mechanism now to construct regular expressions which, like a finite set of finite strings. But we would like to work a little bit harder than that. So Fred's going to show us the clever bit.
So before I do that,
What have I forgotten?
no, nothing. I just want to point out that the way the syntax highlighting works is again here with an or, right? Because we are saying that these things that are in bold, they should either like a from, or they should like a where, or they should like a by. So that's how you use this in practice, right? It's really useful to be able to say I like this or that, right? But okay, let's do the tricky bit. Because so far, we really can't express very interesting things, like Connor said, right? So we can have as long strings as we want, and we can have a finite number of choices of these things, either this string, either from, either where, either by, yeah. But they are very simple strings, right?
Yeah, we can't really talk about patterns of stuff all that well.
So I guess this is where the name regular expression is coming from. So we would like to describe certain very regular patterns. And the regular patterns we like, because they are easy to work with, are the ones where we can take a string and we can match it as many times as we want. So 0 times, or 1 time, or 2 times, or 3 times, and so on. Right? And this is usually called the Kleene star, after a mathematician called Kleene who invented regular expressions. And so if we have a regular expression like this, then we can take its Kleene star, which we want to match 0 more repetitions of the thing, right?
Right. We should be clear that it's multiple matches of the same regular expression. It's the regular expression that gets repeated, not the string.
Yeah. Right. And let's have one of these in real life lines.
Yeah, all star.
Yeah.
So it's a postfix star.
So a typical way to do it is you have a finite number of choices, A or B, and then you repeat this 0 more times, right? So this describes the expression which likes, well, A or B, and then A or B, and then A or B, until you don't want them anymore, right?
I'm old, so I want A or D, with a C on the front and an R on the back.
Right. So what does this match? Well, the first thing has to be a C. Then you get to have as many A's or D's as you want. And then the last thing has to be an R, right?
Yes. So it matches And it matches car and cutter, and it matches, cadader.
Which is Lisp
Yeah.
words.
These are all operators from the 1950s language Lisp, which I learned when I was little.
And so another example of this is to syntax highlight this thing. We are matching as many spaces as we want, and then the word proof, right? So we can have 0 spaces, and we should still highlight it. Could have 15 spaces, we should still highlight it. So it's a star expression followed by something concrete. But okay, we should give the rule, and this is the tricky bit, right? So that's the intuition. But what does it mean to prove that star of P with a capital S likes some string X's, right? Well, there's 2 cases in some sense, right? Either we don't want any repetitions of this expression, in which case, I don't know what we call these things.
I thought we called them none.
By none.
Uh,
And then, is there anything?
Nothing stops you writing a nil instead of X's.
Right. Right. The other thing we could do is I could have a proof obligation which says X's is nil, right?
Yeah.
Um,
Ask will do that much for nothing.
Yeah. So this is one way to do it. Well, if we are done, then there better not be anything left in the string that we like, right? So we could either like the empty string, or we could have one go of P, and then we have more star P's, right? So now we have to think a little bit. So that means that we want to split up this excess into a prefix that matches P, and then the rest of excess which matches star of P again, right? So then that star of P, we could then, if we are done, we use the none rule. If we want to go one more time, then we use this rule, and then we just use this rules as many times as we want until we finally hit the nil case, right? So I guess we should call this sum.
Yeah, and I bake the split into it, otherwise it's annoying.
Right, so you want to give the sum here, right?
Yeah.
So Y's and Z's. Okay, and then, so the first proof obligation is that we really are splitting up X's. And then we want to show that P likes the first bit. And we want to show that star of P likes the second bit. Right. So this can look a little bit confusing because we are now defining what star of P likes in terms of what star of P likes, right? But notice that the string is getting smaller, so we can only use this rule a finite number of times before we are forced to use this rule if we want to be successful in our match, right? Want to talk about this?
Yeah, so I just wrote on the board an equation that says P star is equivalent to, matches the same things as the choice between nothing or a P then a P star. And we could actually just have written that down in a rule. We could have written you can prove likes star P X's by unfolding, by saying prove that likes null or P then star P likes X's. And then you would have had to use the go left, the go right, the split, all of that stuff yourself. But we just saved you that extra left, right, split business by baking them directly into having a choice of 2 rules and building the split into the sum rule. So that's just a little bit of ergonomics. Do you want to do a concrete example?
Yeah. So again, when we wrote the syntax highlighting for ask, then the rule that highlights approve says, well, you should start with a given. Then you get to have as many characters as you want. So that's a star. And then in the end, that has to be exactly proven, right? So that's another instance of this. Do you mean for these to be ors rather than ands?
Well, I meant that to be an or for sure.
Okay. So we have the string ACAB, not standing for anything in particular, I'm sure. And then we have the regular expression, which says it's the Kleene star of A, then B or C, right? So what do we need to do in order to match this? Well, we have to split up this string into chunks of A, then B or C. Right. So we could try to do it with 0 chunks, but this string is not empty, so that doesn't work, right? So that means that we need a first chunk, and that chunk needs to start with an A. That's good, we have an A. And then that chunk then needs to finish with B or C. So I think our chunk better be, this is our first chunk, and then this is our second chunk, right? And that looks good because this is A followed by a C. That's an A and a C. And then the second chunk is an A followed by a B, right? And the chunks, we're not left with any half chunk, then we're just left with nil, so we could finish then. So let's see if we can do this. Right, so we are starting by saying, I want to go around again with a sum. And then I had to say, how did I split this up? And I said I was splitting it up. My first chunk is A then C and nil. Yes, I need more brackets.
Yep.
Let's move this to a new line. And my second chunk is then the rest of the string. Okay, so then I get 2 further goals I have to prove. So I don't have to prove that the concatenation of these 2 things is my original string. That's obvious to ask. But I have to show that my first chunk, AC, matches the expression I'm taking the star of. And I have to show that the rest of it still matches the star of the same thing, right? So let's do this one first. So I'm trying to match an and. So I can do that by splitting up the string again, right, with a split. And now my A is going to match the first thing. So my first string is just singleton A. And then it's the rest. Okay. And then, so it's obvious to ask that A matches the symbol A.
We did that already.
Right. So we just have to do the second one where I have to see, does this expression like C? Well, yes, it does, because it's liking B's or it's liking C's, right? So here I'm going to go right. And then I have to show that SimC likes C, but that's by exact. Okay, so that takes care of my first chunk. Now what about my second chunk? Well, it's a star again. So I have a choice of saying, go round and match with the underlying expression, or use done, but I can't use done because this is not nil. So I'm going to do by sum. And now I have to split it up into the part that matches this expression, well, that's going to be AB. This is my next chunk. Okay, and my final chunk is just going to be nil. I'm done. Okay, and then I have these two things again. I have to show that my chunk is really liked by the underlying expression. But what is this? This is A followed by a B or a C. This is an A followed by a B. So this should be by split A B. And here, B or C likes B by go left, right? This is exact. Okay, and then here I have to show that my star matches something again, but now my string is empty, so I can just say by none.
Okay. That's very cool. So we've introduced all the bits and pieces that are found in regular expressions. Sometimes people throw in a few other things that are derivable. So for example, you'll often find a regular expression that is just one dot, which matches one symbol from the alphabet, but it doesn't matter which one. And sometimes you will see a variant on the theme of star, which is plus, a postfixed plus, which means one or more of these rather than zero or more of these. But that's just P plus is PP star. So those are completely derivable, but they do show up and they are quite useful and compact. How much time have we got? Right, we'll get a bit of nullable done, I think.
Yep. I guess another thing to say that if you use this in the real world, then you sometimes get something that matches the beginning of the line and the end of the line. But you can just consider these to be part of the alphabet, right? So again, that's not anything beyond what we've shown you.
Right. So one of the things we'd like to show you is some machinery that so we've given you proof rules so that you can derive whether a given regular expression likes a particular string. But the whole point, as you can see from the syntax highlighting, is that machines can do it. In fact, it's quite cheap for machines to do it. So I want to work through a construction of a particular strategy for implementing the test for whether a given regular expression matches a particular string. And I'm going to use a strategy which comes from a mathematician called Brzozowski. It was published in 1964. And we will not have time to do the whole story in the rest of this lecture, but we can get to the beginning, or rather the end, because step one is to figure out whether a given regular expression likes the empty string. So that's to say, if the input is empty, look at the regular expression and figure out whether that's okay. So that's what we call being nullable. So the type of nullable is from regex, doesn't matter what their symbols are, to bit. And okay. So you can see our regular expressions are tree-structured formulae. I mean, they're actually very similar to the formula type that we had last semester, except that that had only one variable and it had all the numerical constants. Whereas here we've got lots of symbols and we've got only things that behave like 0 and 1. But it's, you know, oh, and we've got this lovely extra star thing. Okay, but we're going to work inductively over the construction of the formula. And then we're going to have to look at the formula and make our minds up. Okay. So, does fail like the empty input? No, fail doesn't like anything. So that's false. Does null like nil? Yeah, that's the thing that null likes. Do you want to pick one?
Yeah, okay. So sim(x), that was the expression that liked exactly the string, the character x, right? So the string x followed by nil. Does this like the empty string? No, because the empty string is not the same as the character x followed by the empty string, right? So that's false. Okay, so that's easy so far. Let's see.
There's another easy one.
Right. Does star r like the empty string? Yes, it does, right? Because we could go around 0 times, in which case it has to be the empty string. So star is usually the complicated thing with regular expressions, but when it comes to like in the empty string, it's really easy. It just does it. Right. Right. So what about P or Q? So does P or Q like the empty string? Well, it depends on P and Q, surely, right? We can't say. So what if P likes the empty string? Well, if P likes something, then P or Q likes something, right? So if P likes it, then P or Q does. And similarly, if Q likes it, then P or Q does, right? So P or Q is nullable if P is nullable or Q is nullable. So it looks really nice that we're just matching, we're just turning this OR of expressions into this OR of bits, right? It's very aesthetically pleasing. So you could think it's the same thing for the AND, but let's see what Connor thinks about this one.
Yeah. So now we want to remember that P and Q means first a P, then a Q. In the ladies, it's usually the other way around. How can a P then a Q end up being completely empty? The only possibility is that both pieces have to be empty. Right? The only way you can put two lists together and get the empty list out is if the both lists you put in are empty. So indeed, we are turning the sequential AND of regular expressions into the Boolean AND. Okay, so we think we might have some sense that this is the right thing. But what we really ought to do is prove it. And we might get somewhere with that, especially if we cheat. So we have, of course, got some prepared things that, some things we did earlier. But let me which way around do we do it first? We want to prove two things. Well, we want to prove that likes p nil is equivalent to nullable p is true. That seemed like a good thing to do. And well, we actually could just go inductively p here. Why not? Exactly what we didn't do in rehearsal. But we'll knock off a few cases of this and then see what happens when it gets to closing time. So we go inductively p from p, then we get a whole bunch of cases, which I think cases deserve spaces. And we can do the renaming as we go. Okay, so likes fail nil equals this thing. Well, I'm going to do a test because I can see some computation is possible. So far, so business as usual, inductively from test. And if you look at these things on both sides of the equal sign, they are reassuringly both nonsense. Okie dokie. Do you want to get the next one?
Right. Okay. So I'm not thinking yet. I'll just test and see what happens. And then some computation happened. Nullable null was defined to be true. So now I have to prove that this true thing is the same as this true thing. Well, that's also reassuring, right? So I'll do it by equivalence. And okay, that was even easier. Because we just have a rule that says this is true, right?
Yeah.
And it's just true that everything is equal to itself. So I don't even have to give
as your reward, you can do the next one.
Right. So here we have a CMX. Guess I should have renamed it properly. Okay, so again, I'll start by testing to see what I actually have to prove. So this time, my left-hand side, well, it is what it is. So does CMX like the empty string? No, that should be false. And my right-hand side is definitely false, right? So again, I have an equality between two false things. That's great. So I'll say by equivalence. And then I just have to call out the bluffs, saying, well, how could this be possible? Okay. Well, that could be possible if it is the case that nil is equal to something non-nil, but how can that be possible? well, that was impossible. So we are discharging this by pointing out this was just false, right? And similarly here, I'm pointing out that 0 is not 1. So there's nothing to be done here.
Right. And we've got about 5 minutes. Step 1, rename stuff. Okay. Again, first step here is test. Actually, that I hope is a nice way to do this proof. So you can see here that that we know that a Boolean OR returns true. And you can see that we kind of like to know which of them was true, because that will tell us whether to go left or go right. And in the other direction, we want to know whether to go left or go right. And that would be that would be useful. So the funny thing is, I think I would rather have a propositional OR than a Boolean OR. So I'm going to do a very dangerous experiment, and I'm going to prove that A or B is true is equivalent to the proposition that A is true or B is true. That strikes me as a useful fact about bits. And how do I prove that? I first of all look at A, then I test. And I look at these things and I think, some of these things should come out. This one, well, I've got no real choice other than to say by equivalence. Okay, so in this case, I say by, well, I got a choice between proving false is true and a choice, and the other choice is to prove something I've just been given. So, or in introduction, right. Okay. And in this situation, I got to go the other way around. I say from, what use is it to know this disjunction? And the case where it's easy, where the disjunction was true because B equals I, is too easy for Ask to bother with. And to be honest, I should get rid of this one as well. Okay, so 1/2's done. And here, again, I'm going to go by equivalence. And again, one direction is just saying, show a true thing. The other direction is, given a true thing, prove something which we have to make a little bit of a choice to show is true. But if I go left, I'm done. Okay. So let's see if I have a sensible strategy here, which is to say, I wish the right-hand side of this equation was subtly different. Now, we didn't try this in rehearsal. This could collapse around my ears. But that's nice. It didn't. Okay. So this looks like something which is going to work out all right. So I'm going to do this by equivalence. And then here I say, how was this true? Okay. So likes Q nil. I've realized I'm missing a key piece of equipment by doing it this way. I'm certainly going to go right. Oh, sorry, left here. And I'm certainly going to go right here because I've got an induction hypothesis that says that likes Q nil is equivalent to nullable Qi, and I need some more library stuff, namely prove A equals B implies A implies B by implication introduction from A equals B, or A equals A equals B by implication introduction. So that was key fact. And then where was I? I was here. I'm going to do from, and where's my goal? Here's my goal. And what do I want to do? I want to change the P's to Q's. And I can see it's 5-2, so I'll do this case and stop. Right. So what just happened there? I was given this handy fact, and I have to from that. Always with the one at a time thing. Yes. And then that side of the proof is done, and the other one will work out exactly the same. The rest of it, we have to do a bit of guess what? If you chop a list up, if you chop up nil into two pieces, both pieces are also nil. And that's going to be the key thing for the AND case. Also, we will have to prove a few things about Boolean AND in the same way we prove stuff about Boolean OR. The AND case is actually easier, but it's time we weren't here, so we should stop the recording and say have fun with the rest of your day and an excellent weekend. See you next week. Homework coming soon.